parameters multiplied with a dimension. Okay? So work is a moment. That's why we call it fault moment. Why it is so? Just you see these things. The modulus of rigidity, this is expressed as force by length square. This is dimensional formula. This is 4 by length square. Now you are multiplied it with the area, that is the length square. So actually you get the force. Then you multiply it with distance. Then it is force into distance, that is work. Work is energy. Work is equivalent to energy. So if you calculate this thing, these parameters, this fault parameter, this can be easily calculated. We have a lot of techniques to measure the fault parameters. You can easily calculate the energy released by earthquake. Okay? So now once the people actually got hold of these parameters, probably they were suffering from the fear that common people will not understand these things. Do you really believe that common people will understand what is a moment? Richter scale, well, they know that 6 is smaller than 7. 7 means big earthquake, 5 means small earthquake, like this. So what they do, they manipulated the moment in such a way, the number you get, that becomes indistinguishable from the Richter scale, number-wise. But remember that the moment magnitude here, that actually gives you the total energy, but Richter scale gives you the intensity of the energy. So the number what you get actually gives the moment magnitude, this 7.9. If you calculate the intensity of the energy, it will come very close to 7.9, maybe 7.8. So if you put it in this, hardly matters, but the numbers are different. I mean, the meaning is completely different. So this is still hanging, this question. So we have only explained what is the meaning of this 7.9. Now we have to explain whether all the energy is released by earthquake, all the energies released by faulting are actually converted to the earthquake. Fortunately, the answer is no. Why? The energy which is produced because of cracking of rocks, what happens? Cracking of rocks means the bonds within the materials are broken. The moment the bonds are broken, energy is released. And the energy is released not in one form. Usually it releases in different form. One of the form is earthquake waves. There are 3 forms. One part of energy is spent in developing cracks in the rocks, the fault itself. Second part is heat energy. Why? The heat energy it will generate. You know that you have rate friction. That if one part of a material just moves against another material along a plane, then the frictional resistance will generate heat. Okay? And so obviously, whenever there are earthquakes, the heat is generated. And the third part is in the form of earthquake waves. The calculation suggests that the energy, only 30% of the total energies are converted to earthquake energy. So nature is like mother. He may be annoyed with her children, but she will never destroy her children. She develops earthquakes and she has a remedy so that people should not suffer tremendously. Only 30%. Okay? And out of this 70%, heat consumes 65% plus. So most of the energies are converted in hitting the rocks. And how much heat that will be generated? Well, temperature is a thermal state of energy. Unless you are dealing with latent heat case, higher the temperature means higher the heat. Okay. Now, the temperature which is generated because of this friction can be shown by these things. I draw your attention. I think that you are getting little impatient. If it happens, the probably you are in this business like from the morning. Just a few slides. I just draw your attention to this equation. So you need not go into the derivation of these things. If you study in future, if you Google it, you can get it here. I draw your attention to these two parameters, is delta M and delta R. What is delta M? Displacement of fault plane. That is how much displacement it is offering. And what is delta R? The rate of displacement. Okay. So, you know that if you rub your hand, you can do this experiment. If you rub your hand, you feel warm. Now, if you just move it like this, you don't feel like this. But if you move like this, it's warmer. Now, if you move like this, small area but fast, again it is warm. Now, if you move, use whole palm, then you can feel the warmth. Now, if you continue, please don't continue. At some point of time, the temperature will be such that it will burn your flesh. Without any energy, it will burn your flesh. The moment the temperature will be above the boiling point or frying point of the flesh, immediately the flesh will burn. Okay? So, similar thing happens to this. So, faster the motion, higher will be the heat generation. Greater is the displacement, higher will be the energies. Now, if I do a calculation, simple calculation, usually the studies show that usually rock melts between 850 degree to 1000 degree centigrade. Of course, pressure plays a role, but usually it is within this range. Okay. Now, let us see how much energy is required. How much energy is required to melt this rock? I mean, the moment the frictional energy will develop 1000 degree centigrade, rock will start melting. Isn't it? The way the flesh will start burning, the rock will start melting. Isn't it? Now, why there is a difference between Ts and T0? Ts is this temperature. What is T0? That the initial temperature of the rock. Suppose the rock is already in 100 degree, so you have to generate only 900 degree. If you want to take it to 1000 degree. If the temperature of the rock is 200 degree, you have to generate only 800 degree. So higher the temperature of rocks, greater is the possibility of melting. I mean, earlier will be the possibility of melting. Okay. Now if I do a little calculation, if I take the rock parameters and if I see that after the displacement, at what time the rock will start melting? Please, hello.
So what is K?
K is in Kelvin. Degree Kelvin. Which one? This, I explained. This is called diffusivity of the rocks. That is how fast the heat will propagate through the rock. It's a measure of that. It's called diffusivity. I really don't know whether you are aware of this term. Diffusivity is a measure of how fast a heat will conduct through the rock. Now you see, look at these things. Look at these things. If you really want to understand earthquake, and if you really want to understand why earthquake doesn't kill millions or billions of people, you have to understand this equation. And this is the beauty of nature. So you see, if you put all these parameters, usually the fall velocities, the velocities of one block along another block is 1 meter per second. This is the average value. Sometimes it is faster than that. So after 1 millimeter, the temperature will be such that the rock will start melting. Okay. Now at what time? You see the velocity is 1 meter per second. Now after 1 millimeter movement, you see the melting. So if you divide it by this, you get within few milliseconds, fraction of second, it starts, releases earthquake shocks, and the rock starts melting. The moment it starts melting, two things happens. The S wave velocity, L wave velocity, R wave velocity through the liquid are near zero. The moment rock starts melting significantly, it absorbs all the shocks. That is the reason why earthquake doesn't occur for hours. It maximum occurs for 1 minute, 50 seconds, 60 seconds. That means the moment the rock along the fault bed starts melting significantly, it absorbs all these things. The moment, and then this is one part, it absorbs all the harmful energies. The P wave velocity gets reduced by 50%. So basically what you get is nothing, few little jerk. That is how the earthquakes actually taper out. There is a big shock and suddenly there are small shocks, then it stops. This is the phase when the rock along the fault got melted significantly. This is the safety device of Mother Earth. Otherwise, we would frequently get earthquakes about 10, 11, 12 magnitudes. It will never allow the earthquake to reach that level. This is the security measures. Okay? And sir,
you said that when the rocks start melting significantly, then the shocks start.
yeah.
Then why does aftershocks occur?
Yeah, I mean, this is a good question. He says that if this is the scenario that it will absorb all the energy, then what is the question of aftershock? I mean, I have completed the first part, it absorbs these things. The moment it absorbs the energy, there is no movement. Since there is no movement, there is no heat generation. And then that melted rock at 1000 degrees suddenly sees that it is surrounded by rocks having 200 degrees, 100 degrees. Immediately it chills down. Immediately it chills down. So basically this melt actually seals the faults. But remember that the rock is having the strain, it couldn't release because of melting. So then it will try to release the energy. If you can remember the third picture of the cartoon I showed, that there is a displacement but still there is a flexing. So it is in that position. So then what happens? Then again this will try to release the energy, again some melting will be there, and eventually they will die out. Unless and until they come to the last block, the aftershock will continue. But fortunately, now in Nepal all the aftershock regime is over. You probably have read that the aftershock continued for whole of May. Whole of May. But their intensity was much lower than the main earthquake, because most of the energies are already spent, partly by seismic wave, partly by melting. And in the ancient rock record, now comes the geology, we can predict what happens actually at the end. I said that the rock melts and the rock produces glasses. We have to prove that these are the samples collected from depth. And there you see the glass-like material along some fractured zones. These indicates the former place where the earthquake originated. This rock is called pseudotachylite. You need not be bothered with the name. It looks like this. It's glasses with few blocks of rock still present inside. And if you take a thin section, if you make a section of a rock and see under microscope, it is all glass. Why glass? Because the cooling rate will be very fast. You have 1000 degree surrounded by 100 degree or 200 degree. So difference of temperature will be very high. So it will chill very fast. And if it chills very fast, it cannot crystallize material. It will just chill, and none of the spot will have any real crystal arrangements of atoms. And we call this state as glass state. So this is what occurs in the fault planes. Yes, sir.
The shock and the aftershock have same focus.
Yes, mostly, but sometimes it can be different. I mean, you see, it's not exactly the same, but it should be on the same fault. Now, during the earthquakes of May, there were a lot of discussion among different people, different group of experts, whether that should be called an aftershock or a fresh shock. How it is decided? If you Google it, you will find that there are a lot of discussion. Some people said that this is aftershock of the big ones, and some people said that no, these are different earthquakes. They will have their own aftershocks. How to differentiate that? If the focus or foci of all the aftershock lie on the same fault plane, we call it aftershock. But if you see, the fault planes are different. One lies here, another lies 30 kilometers away, then they should be treated as new earthquakes. And of course, they will have their own aftershocks. If you have two new earthquakes, then it is a big trouble. There is a possibility of having the third one. Okay? But fortunately, those were aftershock. In some places were new. So now coming to the Indian scenario, after this earthquake, what happened? Whenever people like me went, the first question, people were so scary in India and of course many parts of the world. The first question they would ask, is there any possibility to have earthquakes here? Sometimes I jokingly said that yes, tomorrow. So some people believe that. They said that nobody can predict when it will happen. But I can tell you the science is that theoretically it can occur anywhere. But scientifically there are zones where the possibility of having earthquakes are more. Why? Because these are the places beneath where you have already some faults. If the material is stressed, they will tend to slip along that fault lines. Okay? And according to this, the India is divided, in fact, whole world is divided into several zones. And here in this diagram, we see the different zones. Deeper the color, showing the more probability of having bigger earthquakes. It's just like heart problem. There is no surety that a person with good health will not have heart attack. But obviously the obese people suffering from cholesterol and blood sugar are the high risk patients. But no doctor can say that heart attack will hit only the fat people. But that is the science. Here also, theoretically earthquake can occur anywhere in India, but possibility of having bigger earthquakes are in these deep zones. In fact, I am showing India, that's why I didn't color the Nepal. The entire thing should be in deep brown. Nepal. Now you see, this is the places. Bihar, Nepal boundary. New Delhi is very close to these deep zones. These are the zones where you should not raise big structures. People like us always tell the citizens of India and Nepal, Pakistan, that these countries are great. You need not enhance the greatness by raising big structures. Actually, by making big structures, you are inviting trouble. I go back to the first slide. They constructed a tower. To show what? And the tower was the first person to collapse. Do you know the name, the capital of Nepal? Do you know the meaning Kathmandu?
Yes, sir.
What?
Sir, it is better.
Made up of what? Made up of wood. I mean, wooden? Mandu means actually mandap in Indian language. They have a pagoda made up of wood. Cut is cut, wood, and this pagoda is made up of this cut. This famous pagoda in Nepalese, the mandap is called mandu. That's why they cut mandu. Didn't they know the use of bricks? Definitely they did. For a Harappan times, people knew the use of bricks and the Nepalese didn't know. Is it possible? Is it possible that the Nepalese didn't know the use of brick some even 400 years back? When the people of India subcontinent knew it some 4,000 years back, but why didn't they do that? Why didn't they do that? Because they observed the earthquake. They know that if they make their mandap with bricks, there is possibility of this structure being collapsed. But modern people suddenly realize that who cares the nature? Let us make big multi-storied building there. And you see the price. You see the price. So these are the zones where you should not install big constructions. Now coming to the moot question, why in Nepal? Some people jokingly said, well, this is very cruel thing, but many people start believing, why in Nepal? Why not in Afghanistan? Why? Pakistan? Why in Nepal? Or why not in Australia? Then the Australian team would disappear. So just hold on, hold your patience for a few minutes. Just hold your patience for a few minutes. Please. So there is a reason why in Nepal. Actually what happens, in the last 71 million years, India is not placed where it is now. It was in the southernmost part of the earth, very close to the present day Antarctica. Then the last 71 years, it just moved like this and then it hit the Eurasian part. And Himalaya was created, you know that. Now I show you another such thing. You see India is coming. Well, it's a ram here. So you see the fractures are coming out. Okay, and now you see this thing. This is Tibet and this is Nepal. Okay, so all along this part you have fractures beneath and India is still pushing. India is still pushing, it is trying to go beneath, the resistance is protecting it, and then you have these fractures. Yes, sir?
Sir, on the very first day, Professor came and he said that our subcontinent, Indian subcontinent is just moving under Tibet. So what will happen in the future if it is a great concern for us?
Yeah, I mean, I'll tell you, that's a good question, but I don't think that I have much time. But very quickly I address these things. You know that the resistance between this part and this part is so high, and you must have seen that some part actually torn out from here and sunk in the deeper part of the earth. So this is the part which actually dragged the thing below. Why the stress was generated? Because this person was pulling it down. Okay, I just replay it. Just you see, here it is coming, now it's hitting and now there is a break. In fact, that part was actually pulling these things below. Now it has torn out. So within few million years it will completely stop. But within that time this will continue. I mean the fractures will be continuously generated and you have terrible earthquakes in future along these shores. Because its density is higher than this one. The density of this material is higher than this one, that's why it will sink. Okay, this is another interesting thing. This is the geologist handling these things, but a calculation suggests that, hey, please. So she was asking why this is going down. Because its density is higher than the density of the adjoining material. That's why it is sinking. Just following Archimedes' principle. So once that part is over, then it will stop. But it will still stop. Geological time is a long time. Huh? What is that part? I mean this part has, where it has gone? Huh? Yeah, actually in every continent, on this earth surface you have two parts. One is continent, another one is ocean. The oceanic part is shown by this layer. Beneath every continent you have a layer which is not oceanic layer, but its composition is very close to but its composition is very close to the oceanic composition. In fact, that person goes down. As it goes down and down, there are phase transition occurring within the rock. Because the pressure is increasing, because depth is increasing, and there are a lot of phase changes occurring here that actually make the minerals more dense than the minerals what you have here. The moment you have this thing, it will start sinking. Okay, and now I do not know how many of you did fly kites. So if you can fly kites, you can feel what can happen here. If it is terrible wind, you see the pull on the thread. At some critical point, this will be snapped and the kite will go. Same thing happens here, just it goes up. Okay, fine. So I conclude these things. Now this is a campaign for future. Just one slide. Please have your attention here. I have said what you should not do. Some of the things which you should not do, but now the do's and don'ts both. You know, the earthquakes and other natural phenomena, they cause calamity, but they cannot inflict disaster. Calamity plus unpreparedness cause disaster. Okay? Human beings have no control on calamity, but preparedness is in our hand. So we can reduce disaster, though we don't have any control over calamity. So what you should do or you should not do first, do not panic and run around madly. I explained why it is dangerous. Second, identify quake shelter. Don't think that I am referring to you move out and take a shelter. I said that you should not do that. Now the question is then what should we do? You should hide beneath the pot. If you use low level furniture, you are gone. If the earthquake hits, then you are gone. Suppose you don't get time to go beneath that. Try to go beneath a table or these things. At least you should stand in the corners or just beneath the frame of the doors, because these are the parts where the building will collapse at the last. Okay. Now you may say, because the construction of the house is less like that, because you have an additional support over here. And finally, these things, do not make big buildings, don't try to dare the nature. Don't try to annoy the nature. And finally, do not allow the dangerous constructions because a little stake will kill it. And finally, indiscriminate water drawing from